Welcome everyone to our AI colloquium. My name is Sebastian Trimpe and I'm very happy to introduce and welcome today's speaker, Angela Schoellig. So Angela is an expert in AI, in particular combining learning, robotics and control. And Angela is originally from Germany, from the Stuttgart region, where she did her master's in engineering cybernetics, and then she moved to ETH Zurich, and that's actually where we first met. So I know Angela since 2008, where we both pretty much did our PhDs in parallel. And back then, Angela was already working on combining learning and control and robotics, in particular iterative learning control, and got this to run, among others, on quadrocopter testbeds. That at the time was one of the first quadrocopter testbed where you could do agile and high performance maneuvers. And Angela's PhD was very successful. Among several awards, she got the ETH medal, which is given only to the best PhD thesis there, and then moved on to become assistant professor at the University of Toronto, where she continued and broadened her research in areas. And that's also shown by the different roles and initiatives that you led, Angela. So for instance, you were also, in addition to being assistant professor and later associate professor at U of T, also faculty member of the Vector Institute, and ran member of the Canadian Robotics Network and University Robotics Institute, showing the interdisciplinary research. And Angela has won many awards, among several of these, the Ontario Early Research Award, Sloan Research Fellowship, and the Robotics Science and Systems, which is the most prestigious robotics conference, the Early Career Spotlight Award. And I guess most recently you got the Alexander von Humboldt Professorship, which is one of the most prestigious awards for scientists in Germany. And it has the positive, let's say, side effect that Angela is also returning to Germany, or has, I guess, officially returned to Germany, accepted a professorship at TU Munich. So today this talk is virtually, as you see, but we also hope to have Angela soon here in person in Aachen. So before we start, just quick mention, as usual, if you have questions, feel free to use the Q&A tool, and after the talk we can have a Q&A session. And with this, Angela, I hand over the virtual floor to you. We are very happy to have you, and very much looking forward to your presentation.
Great, welcome everybody, and good afternoon. It's a pleasure to be part of this colloquium and connect with you all today. Thank you very much for the invitation in my talk, and for the very nice introduction. In my talk today, I will present our research towards robots that safely learn as they operate in the real world. This is actually also my first talk under my affiliation at TU Munich. And I'm looking for exceptionally motivated and ambitious students to join my team as we build kind of an internationally recognized research group in Germany around these topics. I will also remain affiliated with the University of Toronto, and so there will be exciting opportunities and joint efforts between both universities. So let me get started. So just to give you a sense, I started studying control theory in Germany, and control theory is really the field that studies dynamic systems. So these are systems that move or change over time. And then control theory teaches us how we can influence those systems to achieve a desired behavior. So how we can compute this input U to achieve an output X that reflects the behavior we want the system to be. Typically, control theory designs these controllers based on detailed mathematical models, often in this form of a differential equation, as you see it here. And so this is what I studied kind of, growing up during my bachelor's and master's. And if we design these closed loop systems well, then we can achieve behaviors that are difficult to achieve in any other way. And in my PhD, I applied this to flying robots. And this looked like this. So we really were interested in showing the physical capabilities of these vehicles. and to achieve control theory, to achieve precise, accurate, and highly dynamic motions. And so these robots receive commands from a computer 70 times per second, and one mistake could make this vehicle crash. So stability here means keeping this vehicle in the air. And projects in the lab eventually led to collaborations such as this one. This is with Cirque du Soleil, which eventually actually became a show on Broadway from 2016 to 17. In here, the robots are the lampshades. And yes, their motion is pre-programmed and the actor is adapting. So the actor is adapting. But you see, you know, the confidence, the maturity of the technology. So this ran around 350 shows on stage on Broadway eventually. It also reflects nicely what robotics is all about, which means expanding what humans can do and express. Right? And so from that going forward, I noticed that there are limitations when we rely purely on our mathematics models when operating these systems. And since then, I have been leading a research group at the intersection of control theory, robotics, and machine learning. It's a very interdisciplinary group. And if you come to our lab, you don't only see the students working, but you also see robots moving. And I just want to give you a brief impression what type of robots we usually work with, which gives you some context for the research we do. So here our goal is to achieve high performance motions here for a team of flying robots. We do this to show the capabilities of our algorithms, but we also connect this to real applications. So we are, for example, working on applications for monitoring. Here, this is a mock-up nuclear power plant and how these vehicles could be used to monitor the safety of the building. We also fly outdoors using vision in the closed loop. And the goal here is to fly reliably without GPS. Here you see an off-road vehicle we work with, and more recently, over the past 4 years, we have participated in a self-driving competition and built this self-driving car from scratch with a large team of undergrad students, and were successful in winning the competition 4 times in a row. And this is the latest platform you saw at the end, which is a mobile platform with a manipulator arm. So this is kind of the type of robot platforms my team has been working with over the last 5-6 years. And really, you know, we envision a future where robots operate in our human-centered environments and not anymore behind factory walls. And so robots are envisioned to navigate our roads or skies, support us in our daily tasks, and interact with us in the workplace. And in all these applications, robots have to deal with large prior uncertainties. Uncertainties meaning things that we have a hard time understanding ahead of time. For example, the interaction between the robot and its environment. We expect robots to actively make decisions and then, you know, exhibit a safe and high performance behavior. So what do we mean by prior uncertainties? Ultimately, this robot is usually built by us or built by some humans. And so we should have a good understanding how it works and how it behaves. And that is true. And that is why we account for kind of our prior knowledge, often in these equations, as a prior model. But in particular, the interaction with the environment is really hard to model. And that's where we kind of have these unknown effects that can significantly influence the behavior of the robot and limit the performance if we don't account for them. And so, you know, interaction with the environment for a flying robot could be the aerodynamics and the wind gusts. For a self-driving car or off-road vehicle. It could be the interaction between the wheels and the roads, or generally the interaction with other agents. So that is what we try to address with the algorithms that I present today. And then what does safety mean in this context? This is very robotic specific and a specific challenge when we work with algorithms for robots. And one part of safety is state constraints, and that is reflected in this image. So if a robot needs to go to a goal and there's an obstacle in the way, we want to have ideally no collisions with any obstacles in the space. And so you could think of different safety levels, where safety level 1 is that we try to minimize violations of the constraints, which means, we do a trade-off between achieving the task well and satisfying safety constraints. This may not be enough in robotics, right? Because collisions could still happen. So then other considerations or levels that many people consider is probabilistic constraints, which means no violations with very high probability. And lastly, of course, our ideal scenario would be hard constraints, so we can guarantee that we don't collide with any obstacles in the way. Beyond state constraints, you could also, safety also means that we operate the robot such that it doesn't break. So we consider the actuation limits. And in addition, we consider that it stays stable, which means the closed loop behavior remains what we intended to be. For example, for flying a robot to stay in the air, for a driving robot to stay on the lane. And so these kind of safety constraints can be incorporated in this formulation by saying the state needs to be in a certain set, or the input needs to be in a certain set, for example. And so the control approach is that we model the system, we identify possible parameters, and that was kind of the differential equation I showed you before, and then we design a controller. And this works really well in controlled environments. It has advantages such that we can study the robustness towards model errors. So how, up to which error in our parameters are we still, achieving a safe behavior of the robot. And we can explicitly incorporate safety constraints in formulations. So this is a typical approach to control of these robots. The alternative is reinforcement learning, where you start from, usually with a vanilla version starts from nothing, right? You don't have a system model. You directly take data samples and then you optimize the control behavior. And so that looks usually like this. In RL, you talk about a learner or agent, which is the equivalent to the controller. It commands actions and then observes what the robot is doing and how well it does on a particular task, which is reflected by the reward. And then over time and more or less random actions, you learn more about the behavior of the robot and what optimized actions are. This works quite well because you collect relevant data for the task through the reward. You usually optimize the performance in expectation. So it makes it more difficult to kind of consider the worst case, which is something we want to understand in robotics. And it has been shown to perform very well and better than anything else in very controlled environments, which could be, games, these virtual characters, or also very controlled lab environments. So I tried to set the stage on the one hand to explain that there is uncertainty in robotics, and on the other hand that we want safety, right? And that there are kind of two core components: control theory and reinforcement learning. And so we recently did a review paper to kind of understand what the state of the art literature in this area is. And I can And this figure is taken from this review paper, which is called Safe Robot Learning. And so here on the x-axis is the amount of knowledge we have about the system. So we may know the dynamics and the bounds of the uncertainties perfectly, then we are here on the left. And then if we know absolutely nothing about our system ahead of time, then we are here on the right. And in the middle, we are kind of where we have partial knowledge, or which could be just about the structure of the model. And then on the y-axis, we have the increasing levels of safety from no guarantees to soft constraints, which means encouraging safety, to hard constraints, so guaranteed constraint satisfaction. And so if you look at where we want to go, ideally we want to go to the top right. We want expressive models, even for systems we don't know well, and still have safety guarantees. And so, so safety guarantees and flexibility. And so control theory really sits here on the left. So it assumes that we have a good understanding of the model of the robot, possibly with bounded uncertainties, and then it can design controllers that work really well. Reinforcement learning sits at the bottom here. It makes very little assumptions about the underlying system, but then also provides zero guarantees. So it just collects data and learns from interacting with the environment, but things can go wrong during the learning process. And so then in the current literature, there has been quite an effort to fill the gaps, basically. And so the green box are approaches from the reinforcement learning community that encourage safety and robustness, usually by adding some additional terms to the reward that encourage safety and robustness. But there are various different ways how they do this, but usually they achieve safety level 1. So they encourage safety, but there are no guarantees. And there are more approaches, usually driven by the controls community, around safely learning the uncertain dynamics. And a lot of what I show from my own research falls in this category, in the blue category. So you try to learn better dynamics model over time while still providing probabilistic guarantees. And then there are a separate set of approaches I will not cover in this talk that try to certify any learning-based controller by adding a safety filter. So basically, the safety filter will always check is what the learning controller does correct and safe, and if yes, then it will just pass it through, and if not, it will modify it. And so this is kind of the landscape we operate in. And if you want to learn more about this, I encourage you to look at the review paper. And so what a lot of our work falls into this blue category, safely learning the uncertain dynamics. But I do want to emphasize that if you have uncertain dynamics, traditional control can still work really well, right? Just to make sure you don't forget this. So if I have a standard controller and I know my uncertainty bounds, I can design controllers that work really well in a partially uncertain environment, even if I do have these red terms. And so model-based feedback control can be robust to uncertainties, just to make sure you understand that. We just need to have an understanding what those uncertainties are and their bounds. But I give you a few examples. So here, for example, this is purely model-based from our lab with a mobile platform and a robot arm. It pushes this bucket. We don't know the friction coefficient very well. We can also disturb it, and the robot can still, balance the bucket and continue pushing it. Here's another example. This is purely model-based. There's obviously aerodynamic interaction between those robots as they pass through this loop, but still, model-based, pure model-based approaches work. But sometimes you don't have a good understanding of the uncertainty, or if you would incorporate it well, it would make the system very conservative. And so here, this was my very first kind of problem where I looked at learning-based techniques, is when a flying robot is supposed to fly a slalom trajectory as quickly as possible. And so if we don't use any learning and just rely on our models, it does not work, because these aerodynamic uncertainties have a very big impact on the robot's behavior, and not accounting for them well just makes the robot not work well. So a lot of the research I have been doing was around how do we develop safe learning algorithms for mobile robots that push the performance of robots beyond the point what we can achieve with model-based techniques in the presence of uncertainties. And so in this talk, I'll go over kind of three categories. One is around something that control theory people will understand well. How do we design a feedback architecture that helps us achieve this goal of safe robot learning? This comes more from the controls approach. And then I'll talk about probabilistic machine learning models. And in the end, I want to also highlight what we have been doing recently to bring the communities of control theory and reinforcement learning together and think about some benchmarks. So I'll start with the feedback architecture. So I showed you the slalom flying vehicle, and the setup for this, it looks like this. So we have the robot, we have a baseline controller, we send a reference signal to the controller, which represents the task that the robot should do, and we observe how well it does the task by looking at its actual output or actual performance. And so ideally we want R to be equal to YD, or ideally we want R to be equal to Y, and as a result we set R to be the desired output. And so here you see, if we look at this blue line, this is the desired slalom pass that the robot should take. This is, you can think of it looking from the top down, so it's YZ coordinates. And then if we do this repeatedly with just a standard model-based controller, we get these colored lines. And they are all, they're pretty repetitive. So they are all, we do it 10 times, the robot does 10 times the same thing, which is good. So uncertainties to some extent are compensated, and there are always, uncertainties. It's not perfectly starting at the right position. There's a little bit more wind gust, etc. But so this baseline control system makes this robot operate in a repetitive manner. But we have this arrow between the blue line and the colored line. So we have a repetitive tracking error that we want to compensate. And so the first way we looked at this is, okay, we can understand how a sequence of R inputs maps to a sequence of Y inputs. And then we can try to modify the R inputs in a way that ultimately give us the desired behavior at the output. And so we iteratively modify the reference signal in a way that achieves the desired output. And so you can do this through basically a policy gradient method where you use your approximate model of the system. So it looks like this. So you take the reference signal from the last iteration, and then you modify it by looking at how big was the error in that iteration between the desired slalom pass and the actual one of the robot. And then you use your rough model to map this back into how should we modify the reference signal to compensate for this tracking error. And so this model, actually we use a simple model from physics and not a very detailed one. And if you do this, you can show that you can reduce the tracking error monotonically, and there is no stability issues, because as long as you guarantee that the gray box is a stable closed loop system, then and you guarantee that these R signals are bounded, you never have stability issues. So this kind of underlying feedback loop helps you to guarantee stability. And then you can actually, learn. And here we learn above the poles, because you can imagine that initially we would hit the poles. And so after 3 iterations, we are confident that the robot can actually go around the poles. And here you see a different configuration that the robot had to learn from scratch, and you see the learned behavior. A similar approach can also be used to learn triple flips with a quadrotor, where the robot should come back to the position where it started, and in between do 3 times 360 degrees of rotation. And so even for that task, you can do a very similar approach, actually. They use a model to guide you towards a desired reference signal. The advantage of this approach is that you have this underlying controller that helps you, and you use a simple model to as a gradient to show you the direction of correction. The disadvantage is that you have to learn each task from scratch. And so we looked at, can we avoid this by adding this red feedback and basically learning an inverse model. So instead of doing this for a single task, we now try to learn this green box that is the inverse to the gray box, such that the goal is still the same, y desired is equal to y in the end. And this works well because we already have an underlying controller that makes the system operate in a repeatable manner. And our prior knowledge was very helpful in this setup as well, because by roughly understanding what the robot does, we were able to understand what the input features here to this green box, which we model as a deep neural network, but probably many other, regression techniques would have worked, what the inputs should be. And so interestingly, from kind of a dynamic systems understanding, the inputs are the current state of the robot, and the desired output are steps into the future, where R is the relative degree of the system. So basically the internal delay of the system. And so you basically, you don't need a full sequence of inputs, of desired input values. You just need the one that is R steps in the future. And what R is for a particular black box system, you can identify with one single quick step experiment, identification experiment. And then similar guarantees can be provided in terms of input-output stability, but no guarantees on performance really, because it heavily depends on have you gathered enough representative data such that you could learn with a deep neural network and a good representation of this inverse. So that is a bit still an open question, which we addressed in follow-on work, is how do we actively learn this green box from little data, but still have a representative inverse model. And so how did we test this? We wanted to kind of really take it to the extreme. And now this should work for any desired output, right? So we let people draw things on a tablet and let the flying vehicle fly this. And so for arbitrary hand-drawn trajectories, our initial approach that was relatively simplistic, where we learned this green box from periodic tracking data, so circles and spirals, etc. Still, this kind of simplistic approach allowed us to get a 62% average improvement on these hand-drawn trajectories. And again, this green model is learned ahead of time, right? So it's learned once, and then it's an inverse model, and then we keep it like this, and we don't update. So at least not in the basic version of this approach. And so here you see people coming to the lab, drawing things. And the green is kind of the learned version, where the gray is what the system would have done without this correction block. We also use this for ball catching. And so that shows you that this approach can be used as a black box to any system, underlying control system, even if you don't know it. So here, we don't know the detailed low-level controllers in the base of the vehicle or the arm, and we cannot change them, but we can add this additional module to improve the performance. And so here you see, this is a very challenging task. You have to be correct in time and space to catch the ball. And here are a few successful cases. And very close-up view. So it's also very, very narrow opening. So you have to be really, really accurate in time and space to catch the ball. We are not perfect, so for example, here, the prediction error was incorrect. And here the tracking of the robot was not perfect. So we also have to predict the ball, right? And so, but this shows you, like with the learning module, we achieved around 30% improvement in the catching rate, just by improving the tracking of the robot and the arm. And so the exciting thing is that you can really apply this idea to any black box control system, and you should get better. And so the next kind of last thing in this section I wanted to show is what happens if this uncertain component is actually changing over time. So typically in most learning approaches, also RL, you assume there's something unknown, but it doesn't change over time. But that's not true in robotics, where we have wear and tear, change of weather, change of the environment in general. And so what happens if this changes over time? And you can have different philosophies about this, but one way is we replace the standard controller in this baseline control system with a fast adaptation. So it means a very fast adaptation that tries to react to these time-varying changes in a way that the dashed box stays the same. And then anything that we discussed before still applies, and we can still apply it. And so the idea here is an adaptive controller that achieves a linear input-output behavior of this dashed box. And then we can still do the inverse model learning, as I showed you just previously. And we did this architecture, and there can be guarantees around the performance of this fast adaptation loop and how this can work. A very recent work is where we do this fast adaptation through a Lipschitz neural network and can provide guarantees with that. This paper is called Bridging the Model Reality Gap, because you can also use it to learn in simulation and then go to the real world. And this change from simulation to real world can be accounted for and compensated for by this fast adaptation scheme. So this is also a way to do sim to real. And so here's just one example. When we do a similar slalom trajectory with a quadrotor with different underlying baseline controllers, we can learn, this is what I showed you at the very beginning, we can learn the slalom, but then we switch to a different vehicle. So there's actually a discrete switch in dynamics. And if we have a standard underlying controllers like PD or PID controllers, basically the system has to relearn from scratch. But if we have an adaptive controller here, a specific one, the L1 adaptive controller, then we don't need to relearn the task, even so we switch dynamics. So that's very powerful. And so you can also use this to go from a source system to a target system and also change the task. I don't want to go into too much details, but basically these white filled circles show how well we do with no learning. The solid circles show if the target robot learns the target trajectory through iterative training. And these box plots show how the transfer knowledge from a different system can be used. And you see that by transferring information, for example, through some adaptive loop, as I showed you, we can get a 74% error reduction with transfer compared to not learning at all. And you see we are very close to what we think is kind of the best we can do, which are the solid red dots. So this means you don't have to do any training or learning on the target system. You just use what you did from the source system. So overall, all these approaches that I showed you relied on a clever feedback architecture and also relied on ideas from control theory, such as very fast adaptation together with a more high level, low time scale learning. Because of the feedback architecture, we could guarantee stability and give some guarantees around performance, but all these approaches require training phase and cannot explicitly account for state constraints. And so the next section tries to address those 2 points. Can a robot learn as it operates and just get better as it goes? And can we explicitly guarantee state constraints? And as a reminder, state constraints are usually expressed in this form, right? That the state is in a certain set and the input is in a certain set. And the key idea is we still decompose the dynamics into a prior model and then add a component that we want to learn. And for this component, we do make an assumption about how bad it possibly can be. And you can look at this plot at the bottom right. So initially we assume G can be any function in this blue shaded area. And then over time, we get more data about the system and we can reduce the uncertainty envelope. And we use a Gaussian process to model this. And then we use a robust controller to take this uncertain or stochastic model and make decisions that are probabilistically safe. And so that, the typical one we use is a nonlinear robust model predictive control approach, where you formulate the decision-making as an optimization problem. You take into account the Gaussian process. You aim for a probabilistic constraint satisfaction. So the probability of X being in this state set is large. So something like 0.99. And so there have been more recent works. So this is quite active research area. And we and other groups have tried to also provide formal guarantees around stability and recursive feasibility for these type of approaches. But I don't have the time to go into kind of the details of the proofs, but rather want to show you kind of how this looks. And so here you see a robot without learning, and we constructed it in a way that it really hits those the robot hits those pylons because we have model errors. And we used a simple unicycle model, but didn't account for the dynamics of the robot. And then if you use the approach I showed you, initially, the robot is conservative. And it makes sure that over a prediction horizon, which is this purple envelope, over a prediction horizon, it stays within the state constraints. Right? So you see that the purple envelope kind of touching on the constraints. So over we aim for over the next 3 or 4 seconds, we don't want to leave the state constraints. And then as we collect more data, this envelope is smaller, and over the same prediction horizon, we can try faster while not hitting the boundaries. So the prediction horizon stayed the same, it's still 3 seconds, but now the robot in those 3 seconds is predicted to drive much further because it can now drive at a higher speed without the purple envelope hitting the state constraints. And so eventually, you can see here on the left is the first trial through a real off-road terrain, and on the right is the third trial. And all the data collected can be used to reduce uncertainty and drive faster. And so it finishes this part of the path way ahead of what it did in the first trial. So importantly, this approach allows us to incorporate every data point as we collect it, right? So I showed you the first and second and third trial, but just to allow a comparison, but it allows us to incorporate data as we collect it. And we can start the robot in a safe operation state, and then just optimize performance as we collect more data. There are many open questions around these type of approaches. A lot is also around how we simplify the optimization problem to achieve faster computation and therefore longer prediction horizons. And we have a number of different works in this area. One I want to emphasize briefly is of Melissa Greve. She's soon defending her PhD thesis, and you can see her work where we leverage differential flatness, a certain dynamics property of many robots, to make this a very tractable problem. And you can also do this in a more formal setting. And I point you to a safe model-based reinforcement learning paper we did, where we kind of incorporate these ideas of Gaussian process in a full reinforcement learning framework. And one more practical approach with Gaussian processes that is slightly different to what I've showed you is you can also use them to safely and automatically tune controllers. And everybody who is a controls engineer in the audience knows, like, tuning controllers is not easy. We usually do this manually. I usually have to do it again on the real system, even so we tuned it in simulation. And so here is some work where we leverage safe optimization based on Gaussian processes to optimize the 2 controller gains of the controller by measuring the performance on this particular task. So it's very task dependent. And so here you see the end, we found the optimal gains for this. But again, this is still more of a toy problem, right? Where we optimize over 2 parameters. So overall, these type of approaches allow us to operate the robot from scratch, like without a training phase, and explicitly incorporate state constraints. I still want to emphasize that all these approaches still to provide guarantees make certain assumptions, right? Otherwise, there's no way you can provide guarantees. But they are they combine ideas from reinforcement learning and control theory or machine learning in general and control theory to improve the performance of robots in the presence of uncertainties. And so the last part I want to briefly talk about is our efforts around creating a community and benchmarks in this area. And so the first one is we recently published this paper on safe learning in robotics, where we consider both approaches from the control theory community as well as the reinforcement learning community. And I think really both communities are really driving this topic. And often there's no exchange between these communities and a lack of understanding of each other's approaches. And so we tried to, give an overview of the state of the art in this review paper and also include some open source code where we implemented some approaches from the controls community as well as from the reinforcement learning community. And this led to our next effort to open source all of this code and implement more approaches from both the controls and the reinforcement learning community, approaches that work on, that consider safety and could eventually work on real robots. And so this is a simulation environment. There are more than 12 type of approaches implemented right now. And I also saw some first papers using it to evaluate their approach. So I really encourage you to look at this. I think it's a great way if you develop something new and you want to compare it to existing methods, right? Those existing methods may already be been implemented in safe control gym, and hopefully comparisons this way are easy and you save time by using it. That's our goal. The key addition in this benchmark suite is that you can explicitly define constraints, such as state constraints, and explicitly define prior knowledge. So we can also answer questions of how valuable is prior knowledge? How much data can I save? Or by incorporating my prior knowledge instead of learning from scratch. So I'm really happy to answer questions around this topic or connect you with the people who have implemented this. We really hope that people adopt it and contribute. And if you code your approach up in this framework, you can make it open source and other people can benchmark against it. There's lots of other efforts. In particular, we have a workshop at ICRA next week on Friday on basically benchmarks and simulation and how to eventually move algorithms to real incorporate these kind of learning algorithms in real products in the real world. And so look out for the ICRA workshop this Friday. I'm also giving a talk on the safe control gym benchmark suite, just the code base, on Monday next week at ICRA. And other efforts that we are doing are all on saferobotlearning.org on the webpage. There have been previous workshops and all the workshop talks are online. So there are quite a few resources by now. You can also sign up to a mailing list there. So to conclude, one way to look at this overall area of work is that in robotics, we often have relied on models and we understand very well how good the models are and where they are accurate enough for the robot to operate. So we know the part in the world where the robot can navigate safely based on our prior models. And then we can provide strong guarantees in this small kind of green area. But generalization to new contexts is difficult. Then, general data-driven approaches learn from data, have usually very general models, underlying models that are expressive, but we often don't understand where the model is a good approximation of the real world and where it's not, where the boundaries lie. And so a lot of the safe learning in robotics tries to combine both we want to expand the green area, but we also want to know or have a good understanding where the learned model is a good model and can be used for decision making. If you look at our review paper, we formulated this whole area of safe robot learning as an optimization problem, because that kind of was the easiest way to connect reinforcement learning and control theory. I don't want to go into all the details, but ultimately we then define the safe learning problem as a problem of mapping prior knowledge and data to the best decision-making policy pie or the best controller pie. So combining both prior knowledge and data for the best control. And there are lots of open challenges, and they are highlighted in the paper, but I want to just emphasize that this is really exciting, and we have lots of work to do to make these algorithms really useful for robotics products in the end. And one is, and there's a typo, product class of systems. So none of the approaches today consider hybrid dynamics or soft robotics or partial differential equations. They all make the assumption that we can measure the full state, possibly with a bit of Gaussian noise, but they don't consider that we may have just images as measurements, or other high dimensional sensor data from multiple sensors. And we also need to solve the state estimation problem as part of this. So all of them assume right now somehow you have a good sense what the robot's current state is. Many of these approaches are also not ready to be scaled to large scale systems, and are not necessarily sampling efficient or computationally efficient. In robotics, this really matters, right? Because you need to make decisions at high rates of sometimes 100 hertz or higher. And then, as I said, if you want to provide guarantees, it all relies still on some assumptions, and verifying that these assumptions are correct and possibly adapting them is also something that is not done in these approaches. And so lots of work to do, but the core, I think, that is that many of these approaches combine some models with data. And I think this is also the key to eventually achieve high performance and safety in these embodied physics systems that are actual real world systems moving and in the real world. And so I think there's a really exciting area of applying machine learning in robotics, because it has challenges that typical machine learning applications don't have. One being safety, another one being that we really aim for data efficiency, because data is expensive, and that these systems are operating in the real world where the environment can change over time. So thanks everyone. I'm very happy to answer any questions, and this is a team picture and our URL of the lab.
Great. So Angela, thank you very much for the very clear and inspiring talk, and I can certainly recognize many problems, and I certainly agree that this is exciting and lots of work to do, but also lots of opportunities.